Another method in place of Newton-Raphson in looking for the roots of nonlinear equations is Secant method. Learn how it works here in numerical solutions to C problems. Let's have a quick background of the method's concept before we solve for a root. Given a function, we are to look for the x-intercept of an interval. Saying that we already have the initial values, they are illustrated as point A with x distance of xa and y distance of f of xa. This point is taken from an assumption. The second point is also assumed, and from the illustration, the x distance is xb and its y distance is f of xb. Since Newton-Raphson uses differentiation, which we are trying to avoid in this method, we will use secant line instead of tangent line. This line connects the two limits. We need to derive the function of the succeeding x values until we reach the root. First, we separate the numerator from the rest of the second term of the function. The denominator is where f prime is. Instead of using calculus, let's just take the computation of slope using 2 points. By taking the small triangle created by the secant line, we take the rise of the triangle as f of xa, less f of xb. The run is also taken as xa minus xb. Plug this slope formula into the function, then flip the denominator down below. This function is used to determine the x location of the succeeding x in the iteration. The problem to illustrate this method is a simple polynomial where f of x is 5x cubed minus twice of x squared minus 4. The root of concern is nearest the origin, in the positive side. Accuracy requires 4 decimal zeros, and the initial values to be assumed are whole numbers. Like any other methods, the initial values are found by assumption. So since we are looking for the roots nearest the origin, we can assume x of 0. If this is plugged into the equation, f of x turns to be negative 4. Since we are searching for a positive root, let's assume x of 1, where f of 1 turns to be negative 1, another negative, which means we need to assume some more. Say we take x of 2. F of 2 comes out as positive 28. Finally, we see the sign jump, so we are certain that the root lies between x of 1 to 2. Placing the initial values into the table, we create one with 5 columns including the iteration number. This time, the first column is the left limit, followed by the right limit, and then their functions, f of the left and f of the right limit. To use the derived function easily, these columns are tagged as xa, then xb, followed by f of xa and f of xb. From the previous computation, we had the left limit as 1, and the right limit was 2. F of the left limit was negative 1, and the function of the right limit was positive 28. Let's then start the iteration. The second xa is just the old xb, which means the old f of xb replaces f of xa. The succeeding x is solved using the function we derived, where we have 1 less negative 1 times the ratio of 1 less 2 over negative 1 minus 28. which turns out as 30/29, or 1.034483. This is the new xb. The function of xb is then computed using the equation, that is 5 of 1.034483 cubed minus twice of 1.034483 squared minus 4, which becomes negative 0.60502. Continue the next iteration by sliding xb into xa, and also their function. Then, take the new x of b using the derived function, which then turns out as 1.054905. Plug these into the function. F of xb then is taken as 5 times 1.054905 cubed minus twice of 1.054905 squared less 4, giving negative 0.35603. The fourth iteration then starts with the new xa of 1.054905, and f of xa is then negative 0.35603. The new xb is then computed as 1.034483 less negative 0.6050024 times the ratio of the difference of x values and the difference of f of x values. The new xb is then taken as 1.084105. Take this value of x and plug it into the function, and then come up with f of xb, which turns out as negative 0.0287. We already have 1 0, so we keep on iterating. We again slide xb into the new xa, and also f of xb becomes the new f of xa. Then compute for xb using the secant formula, which results to 1.082546. Now compute for f of xb, plugging 1.082546 into the function to have negative 0.0006. Moving to the next iteration, slide xa and f of xa once more. xb is then computed as 1.084105 less negative 0.0287 with the fraction of 1.084105 minus 1.082546 over negative 0.287 minus negative 0.00062. And this gives 1.082591. Plug this value into the function to get f of xb as negative 0.00006. This is very close to y of 0, as it already exceeded 4 decimal zeros. So we can say at this point that the root of the function is at x of 1.082591. In case we take another iteration, xa then is the former xb, and also f of xa was the previous f of xb. Take the new value for xb using the secant function, where it gives 1.082591. Substituting this value into the function, f of xb is then solved as negative 0.00006. And from the two columns, we can then observe a convergence. Thus, the root is certainly 1.082591. Now let's also show what happens when the columns for the limits are interchanged. From the table, the second column is the right limit, followed by the left limit. So from the initial values, we write the right limit of 2, followed by the left limit of 1. Their functions are solved earlier as 28 and -1. The procedure of secant method remains the same in the iteration, where the start is to slide xb as the new x of a, as well as their function. The new xb is then solved from the secant equation, which is 30 over 29 or 1.034483. With this value plugged in to the function, f of xb is shown as -0.60502. The third iteration has xa of 1.034483 and f of xa as -0.6052. The new xb is then computed from the secant function, giving out 1.087304. f of xb is then solved as -0.062757 when xb is plugged in the function. Keep on iterating, so slide xa as 1.087304 and f of xa of -0.062757. The fourth iteration xb is computed as 1.034483 less -0.60502 times the ratio of the difference of the x values and the difference of the f of x values, which turns out as 1.08234. This value then gives f of xb as -0.00333. This time, we have two decimal zeros. The next iteration follows the same pattern of sliding xb and f of xb as the new xa and f of xa. The new value of xb is then computed from the secant function, which gives 1.08259, and f of xb uses this value to have -0.000019. This value already meets 4 decimal zeros accuracy, but we keep on iterating as we try to check if we can have the same root even if the columns in the table are interchanged. The next iteration has xa of 1.08259. Then, f of xa is -0.000019. The new xb is solved as 1.082591 using the secant function, and f of xb is then solved as -0.0000006. Again, we arrive at the same f of xb from the left-right arrangement of the columns, giving more than 4 decimal zeros, where the root is the same with the earlier answer of 1.082591. If we iterate once more, xa is then 1.082591, and f of xa is -0.0000006. Solve for xb, where it turns out as 1.082591, giving the same value for f of xb as the previous answer. Now it is seen that xa and xb also converge, giving the same root as 1.08251. This shows that no matter what arrangement is used in the columns, the slide route remains the same, where the root would remain the same.